Today we're going to do 3.1, reciprocal of a linear function. We've already learned how to graph reciprocals of linears and quadratic functions, and today we're going to take it a little bit further. So we're going to be able to determine the equation of a function that is a reciprocal of a linear function given its graph. We're going to be able to identify key features of rational functions that are reciprocals of linear functions, and we're going to solve problems involving rational functions that are reciprocals of linear functions. All right, let's get started. So the reciprocal of a linear function f of x takes the form 1 over f of x. You know that. And here's the first example. It just gives you a graph and it says determine the equation of g of x below. Well, you can see quite easily that this is a reciprocal linear function because it has those two branches. They're on opposite sides of the x-axis. So we are going to get an equation 1 over a linear function. So there's a couple of different ways to do this, and I'll show you both methods and you can decide which one you want to use. So method 1 says just come up directly with the equation of the reciprocal function. So you're going to use this generic equation, g of x equals 1 over m times x minus s. Now this is interesting because normally when we have the linear function, let's call it f of x, it would have been in mx plus b form, right? Linear, normally. But we don't use the b here. We use m and we factored it out to get this s. And this s really does represent the vertical asymptote, okay? All right, so it says sub in any point from the reciprocal function to find m. Well, first we're going to sub in the vertical asymptote. The vertical asymptote in this case, it's a little tricky because I divided the scale not into whole numbers, so we can see that the vertical asymptote goes through right here. This every third square is represents 1 unit, so this is a third, 2/3, 1, 1 1/3 is our vertical asymptote. So this is x equals 4/3, better known as 1/3. All right, so we're going to start by subbing that value in for s. So s equals 4/3. So g of x is equal to 1 over m times x minus 4/3. Okay, and then you're going to take any point on either branch and you're going to sub it in and solve for m. So if I were to look at this one, I would say the point, what is that? This point is on the graph, this point is on the graph. So I guess this point is probably the easiest to use. That's the point 1, -1. So we're going to sub that point in. So -1, so I'll just say sub in 1, -1, and we're going to get -1 then equals 1 over, we don't know m, but we know x is 1 minus 4/3. There we go. All right, now we're going to solve this. This one's a little awkward, right, because our variable's in the bottom. That's okay, because we can just cross multiply. So this is like over 1, and when I cross multiply, I get -1 times m times 1 minus 4/3. Maybe what I'll do before I cross multiply, is just simplify this. So 1 minus 4/3 is -1/3. So this is going to be m times -1/3. I'm just going to maybe clean that up a little more. Let's just move our work up here. So this is going to be -1 equals 1 over -1/3 m. Normally we write the coefficient in front. Now I'm going to cross multiply. Sorry about that. And when I do that, I'm going to get 1/3 m equals 1. And so dividing both sides through by 1/3, I get m equals 3. 1 divided by 1/3 is 3. What is my equation? Therefore, g of x is equal to 1 over 3 times x minus 4/3. Now I would probably prefer you to expand that out. So let's give it in at y equals mx plus b form on the bottom. So this is going to be 1 over 3x minus 4. I think that's better. Okay, so always give it so that it's expanded out, but you have to use the factored form to be able to put the vertical asymptote in. Okay, so that's not so difficult, right? All right, let's try. I think the therefore should go here. We really shouldn't have had this because we didn't simplify it. Is the equation of the graph. Okay. Second method. The second method is to actually come up with the linear function. And if you can come up with the linear function that generated the reciprocal function, then you just write it as 1 over that linear function and you've got your equation of your reciprocal function. So if we go back here, we knew from our rules for graphing linear reciprocals that at 1, where y equals 1, and where y equals -1, these are points on our line as well. So I've already identified them here. So y equals 1 right here, I go over, that's a point on our line. And at -1, this is also a point on our line. So I'm going to, no, I'm not even going to bother trying. I was going to try and do it freehand, but there really is no point. That's really not great. So I'm just going to try and fix it, but that's our line. So there we go, that's a little better. Okay, so I've got this lovely line. I'm going to just make it red. Okay, so I'm now going to come up with the equation of that line. Super easy to do that, right? I've got 2 points. You remember your slope formula from grade 9, hopefully. So if you have 2 points, this is the point 1, -1. We figured that out already. This is the point. Let's see, this is 1, this is 1 1/3, this is 1 2/3, better known as what? 1 2/3 is 5/3. And we went up 1. Okay, so if I'm going to come up with the equation of the line, I'm going to use 5/3 1 and 1 and -1. So the slope, well actually I'm just going to write these 2 points down. 5/3 1 over 5/3 up 1, and then 1 and -1, I believe it was. Okay, so these are 2 points on our line. Just write that down. Okay, the slope then is y2 minus y1 over x2 minus x1, as you recall from way back when in grade 9. And you're just going to sub in y2, start with this one, -1 minus 1 over 1 minus 5/3. So the slope is -2 over minus 2/3. And if I'm writing that as a proper fraction, that's going to be -6 over 2, which is +3, -6, sorry, over -2, +3. Okay, so I've got the slope of my line. Now I'm just going to write it as y equals 3x plus b. I'm going to sub in either point. Of course, I'm not going to use the fraction. 1 -1. and I'm going to calculate my b. So negative 1 equals 3 times 1 plus b. Negative 1 equals 3 plus b. And my b is negative 4. So the linear function, let's see what we called. I think we called, take the reciprocal to find g of x, so we're going to say f of x (3x minus 4), and the reciprocal function is 1 over 3x minus 4. See, I should call it g of x. Okay. Not too hard, right? Second example says refer to the first example and use interval notation to state the domain and range and where the graph is increasing, decreasing, positive, and negative. Okay. So, let's just look at this one. Do you remember the rules that I went over quickly about graphing reciprocal linear and reciprocal quadratic functions? One of the rules was that the areas of increase on the original are the areas of decrease on the reciprocal, and vice versa. So let's look at this. We can see that if we look at our original, which is the red, as we sweep from left to right, this graph is increasing, right? The y values are going up the whole way. If we look at the next graph, we can see that the blue graph, the reciprocal, as we sweep this way, they're going down. It's decreasing. Now, it stops decreasing. It looks like it increases here, but it actually just hops over the fence and starts decreasing again. It doesn't start decreasing from here because this is approaching negative infinity, but what it does is when you get over the asymptote, it is decreasing again as we go along this way. So this graph is decreasing over the interval from negative infinity to x equals 4/3, not including 4/3, and then from 4/3 to infinity. We also talked about the areas where the graph was negative and where the original was negative are the same areas where the reciprocal will be negative, and vice versa. So wherever it's negative on the original, it's going to be negative on the reciprocal. So let's think about that. This graph, you can see, is below the x-axis, the red one, all the way until it hits this asymptote, and then of course it is above the x-axis after that. So it is negative until it hits x equals 4/3. At x equals 4/3, it's neither negative or positive. Remember, it's Switzerland, and then it's positive thereafter. So is that true for the blue one as well? Let's look. It sweeps along here. It's below the x-axis all the way along here from negative infinity, and then again the graph is not negative nor positive at the vertical asymptote, and so we would stop it at 4/3 with a round bracket, and then it's positive from 4/3 over to infinity. Okay, those are the intervals. And then it also asked for the domain and range. So if we wanted the domain and range, we would look at the blue. We're just going to do it for the blue one. The domain, of course, is everything but 4/3. So we would write that as negative infinity to 4/3 round bracket, and then round bracket 4/3 to infinity for the domain. And then the range, start with the bottom and work your way up. So goes from negative infinity to 0, not including 0, hops the fence, and starts up again at 0 all the way to infinity. Okay? All right, so let's get that down. It says use interval notation to state the domain and range. So we decided the domain was negative infinity to 4/3, and then 4/3 to infinity. The range is negative infinity to 0, and then 0 to infinity. So that's the domain and range, where the graph is increasing and decreasing. All right, let's start with increasing. So if we quickly go back, where is the blue graph? That's the one we're talking about here, because that's the reciprocal function. Where is it increasing? Well, we decided that as we swept this way, so think of a big line. Let me just draw a line here. So start with a vertical line, and if I pick up that line and I sweep this way, the blues are decreasing as I sweep this way. And then I hop the fence here at the asymptote. They're still decreasing even though they've markedly gone up. It hasn't increased. It's just that this branch starts from infinity and it continues to decrease as we move. Okay? So it's not like it's increased from here to here. Okay? It's just a new branch and it is now decreasing as well. So it is decreasing from negative infinity, let me just get back there, to the 4/3, and it never increases as we discussed. So we're going to say negative increases never, and it decreases from negative infinity to 4/3, and from 4/3 to infinity. It's not increasing or decreasing at 4/3 because of the asymptote. Okay, now let's go positive and negative. So what was the interval for which the graph was positive? Well, we can see that the graph was positive from 4/3 to infinity, and then the graph was negative from negative infinity to 4/3. So back we go. And so that's going to be positive from 4/3 to infinity, and negative from negative infinity to 4/3, round brackets. Okay. Example 3. The time required to fill a reservoir with water from a hose is inversely proportional to its rate of flow. When the hose is flowing at a rate of 18 liters per minute, it takes 14 minutes. Part A says, write a function to represent the time as a function of the rate of flow. All right. What we have here is we need some let statements. So we're going to let's just read it again. It says, write a function to represent the time as a function of the rate of flow, which means that our dependent variable is going to be the time, and the independent variable is the rate of flow. So let's let R represent, it's like our X, the rate of flow, and our units are going to be in liters per minute. And let, because it's a function, we'll use function notation rather than just another letter. So how about capital T of R represent the time, because the time is a function of the rate of flow. And we'll say in minutes. Now I'm going to use these two variables to come up with an equation. And let's just go back to where it says inversely proportional in the original question, and let's talk about what that means. So if two entities or two variables are inversely proportional, what it means is that as one of them goes up, the other one goes down. And mathematically what it means is that r times t of r is a constant. And we use k as our constant. We call that the proportionality constant. Proportionality constant. Okay? So this product here is always going to produce the same constant. So if r, it goes up, it stands then that t of r must go down. Or if t of r goes up, r must go down in order to maintain this constant value over here. So if I take that notion there and I want to write this as the time is a function of the rate of flow, I'm just going to divide both sides through here by r. So we've got t of r is equal to k over r. That's our generic equation for the function, but we want to actually figure out what k is because we have some information here. So we're going to sub in for the time, it's 14 minutes. We don't know our k, but we're going to figure it out in a second. And the rate of flow is 18. So in order to solve for k, I can just cross multiply, and I'm going to get k equals 252. So our equation is t of r is equal to 252 over r. Okay? All right. Now it says sketch a graph of this function. And so there's a couple of ways that I can do this. Just when you're looking at this, 252, you think about it from a transformations perspective, we've got 252 times 1 over r. Think about it, the 1 over x business, right? This is y equals 252 times 1 over x. So this is a vertical stretch by a factor of 252 of your base function 1 over x, which would be your basic reciprocal function. Okay, you could do that. Or there's another way you can think about it. If you wanted to think about it in terms of reciprocal functions, you could rewrite this so that it has a 1 on top. So 1 over 252. What does that equal? Basic rules of division of fractions say that you flip this and multiply. So if I flip this and multiply by 1, I'm going to get 252. All that to say that I can rewrite this as t of r then equals 1 over 252 r. So if I wanted to use our rules for generating the graph from the linear function, our linear function would be 1 over 252 r, and then we could generate the graph from there. So two ways to graph this, but because we've done it sort of this way by graphing the linear first, we'll go ahead and do it that way. Now I know that rate of flow and time have to be positive, so I'm really only concentrating on the positive quadrant here. And if I'm graphing y equals 1 over 252r, then what am I doing? This is the slope of the line, so I would go up 1 and over 252 if I really wanted to do that, right? Okay, so I'm just going to say this is I'm just making a rough sketch here. I'll go over, this is 100, 200, oopsie, this should have maybe gone a little terrible here. Okay, so 100, 200, and 300. Okay, so if I wanted to graph this, one of the points, 0, 0, Another point then, up 1 over 252. So here, pretend it's there. I'm going to graph this line. I'll use my graphing tool here. Yes. So that's going to be this line here. And then I'm going to generate my reciprocal. So my reciprocal, sorry, I'm just trying to get my pen back. There we go. My reciprocal, I generate, remember, from the zeros. So I know that there's going to be an asymptote at x equals 0 here. Here, I'll just kind of sketch it in. So x equals 0 here. I'm going to, at where y equals 1, I'm going to go over, and I know this is a point on my reciprocal function. I've got these asymptotes at y equals 0 and at x equals 0, so I know this is a graph that's going to approach the vertical asymptote and approach the horizontal asymptote. It's not going to cross the y-axis, and it's not going to cross the x-axis. Okay, so this is the graph of y equals, let me just get it right here. I can either write it as 252 over r, maybe I should use t of r, sorry, equals 252 over r. This is the graph in the black of y equals 1 over 252 r. Okay, the linear function. If I were giving full marks for this, I would, because you've only got one branch, I'm only going to expect 1 point labeled. So this is the point 252 and 1. And you've got your equation. I put the equations on there. Okay. We should also, because this is a real life word problem, oopsie, sorry, label the axes. So this was the rate of flow in liters per minute, and on the left here was the time in minutes. Okay, so let's move on. Oopsie. How long in minutes and seconds would it take to fill the same reservoir when the hose is flowing at a rate of 10 liters per minute? Well, we know our equation was T of R equals 252 over R. And that 252 does not change because the rate of flow has changed. What's going to compensate is the time then, right? The time will change. So T of R is equal to 252 divided by the rate, which is 10. So T of R is 25.2 minutes. But the question says, how long in minutes and seconds? So what's 0.2 of a minute? It's not 20 seconds, okay? So if you have difficulty with these kinds of questions, you could just convert 0.2, which is really 2 out of 10. Instead of 0.2, we can just say 2 out of 10 equals x out of 60, right? How many seconds is 0.2 of a minute? And so 10x equals 60 times 2 is 120, and x equals 12. So 0.2 of a minute is actually 12 seconds. So in minutes and seconds, we could say it will take 25 minutes and 12 seconds to fill the reservoir. All right, there we go. Okay, it says describe the rate of change of the time as the rate of flow increases. So if we go back to our graph, we can see that if we are moving from left to right, the rate of flow is increasing. And what's happening to our y's? They're decreasing, right? So as the rate of flow increases, the time decreases. And that just makes sense intuitively, because if you're going to increase the rate of flow into a fixed volume object, you know then that the time is going to decrease, right? So the time is decreasing as the rate of flow increases. All right, that is all she wrote. Thanks for listening. Good night.